So first of all, I would like to say that I'm honored to be able to speak here in this conference celebrating 90 years of quantum theory. I've been asked by the organizers to present a kind of pedagogical overview of quantum gravity, or it's rather going to be mostly quantum supergravity in this talk, and this is what I will do. I've recently published an article in the recent issue of CERN Courier, so if you want to read more about my personal views on this, so this is one place where you can look. So we are here to celebrate 90 years of quantum mechanics, and as we've heard yesterday, quantum mechanics is the most successful, best tested theory in all of physics and in all of science, as testified by the talks at this conference and also by David's review yesterday. And in particular, what should be mentioned here is the standard model of particle physics, which continues to be valid as far as it's been tested. But I would also like to say that general relativity, although it's not as well tested, is catching up rapidly. As you've also heard in Thibault's talk, there are numerous tests over a vast range of distances, and in particular, there's direct detection of gravitational waves. And so far, experimental searches have found no deviation whatsoever from these theories, despite a great deal of effort. And still we know that both the standard model of particle physics and general relativity are incomplete theories, despite their overwhelming success in explaining phenomena of a vast range of distances and energy scales. So this has led to the conviction that both theories must somehow be replaced by a deeper, more complete theory, a theory of quantum gravity. So let me briefly review the reasons why we should be interested in a theory of quantum gravity. And it has to do with the occurrence of singularities on both sides, in general relativity and in quantum field theory. In general relativity, it's very well known that the occurrence of singularities, gravitational collapse, is a generic phenomenon. There are singularity theorems that tell us that space and time end at the singularity, and at that point the theory does not tell us what to do. And of course we would also like to find out what happened at the moment zero, the moment of the Big Bang. The question is also, what is the structure of space-time at the smallest distances? On the other side, in quantum field theory there are also singularities. As you know, there are, in perturbation theory, the ultraviolet divergences in Feynman diagrams. We've learned how to deal with them in terms of what's called renormalization theory, which gives fantastic predictions, as we've heard, but these are order by order in perturbation theory. And it is not clear whether the standard model or any of its field theoretic extensions actually exist in any sense beyond perturbation theory, and this has motivated the search for what's called an ultraviolet completion of the standard model. Now, I think the difficulties probably have a common origin. Namely, first of all, in quantum field theory, as you know, elementary particles are treated as mathematical point-like excitations. This is the origin of ultraviolet divergences. And at the same time, we also treat space-time as a continuum differentiable manifold. Now, when you think about quantum theory, there's certain granularity, and this has led to the expectation that in a theory of quantum gravity, also something dramatic must happen to space and time at the Planck scale. This is actually a conviction that most approaches to quantum gravity share, with the possible exception of people advocating asymptotic safety. So here's a sort of picture of all the parts. There are all kinds of ideas how this might happen. So it's the question, is there a granular structure of quantum space-time? Are there space-time atoms? What does string theory have to say about this? There are also alternative approaches, loop quantum gravity, from which this is the way a loop quantum gravity person dreams about quantum space-time. Or it might even happen that at the Planck scale, the very notions of space and time no longer make sense, in the sense that space and time might disappear or de-emerge. Now, the question is, of course, why don't we go and look? And the problem has to do with the scales. The basic units of for quantum gravity were already calculated by Planck before actually the invention of or discovery of quantum mechanics. It's also remarkable that in his paper he says that he notices that you can form these quantities from h bar g and the speed of light, and he also says that these are numbers that also an alien civilization would calculate in exactly the same way, and it is at these scales that quantum gravities are expected to manifest themselves. So there's clearly no hope of direct experimental tests. There's no hope for a gravitational analog of the photoelectric effect, for example. So a key challenge for any proposed theory of quantum gravity is to offer quantifiable criteria to confirm or falsify the theory. And as there are numerous approaches, these proposals must in particular allow to discriminate between different proposals. A further aspect of this problem is the so-called hierarchy problem, the fact that the gravitational force is so much weaker than matter interaction. And this is also reflected in the spectrum of elementary particles. The question is, what keeps the masses of the known elementary particles so tiny in comparison to the Planck scale? Well, there's also a question how gravity is related to matter. This is Einstein's equations, and this is what Einstein himself said about his equations. Left-hand side is pure geometry, so it's marble. Right-hand side is timber. We don't quite know what to put there. And as you perhaps know, the last 25 years of his life he spent trying to understand the right-hand side of his equation geometrically. So ideally we would like to move in the unification program somehow the right-hand side to the left-hand side, combine everything into some kind of beautiful geometry. And there's been some progress in this direction. I'll just mention two things. Kaluza-Klein theories, namely the idea that space-time might have more than 4 dimensions, and the extra dimensions beyond 4 viewed from 4 dimensions would really manifest themselves as matter fields and matter interactions. And the other idea is supersymmetry, whereby one adds, in some sense, fermionic dimensions and fermionic geometry to sort of understand or make more beautiful the right-hand side. There's also the question whether gravity reacts back on quantum mechanics. Do we have to change the rules of quantum mechanics in order to incorporate gravity? This we heard about yesterday from Gerard. There are 2 points here. One, there's of course issues to do with information loss and black hole evaporation. You've heard about firewalls. I think this debate so far has been inconclusive. But I would also like to point out that in scenarios with where space and time somehow disappear, one could also ask questions like, how does this affect issues of quantum non-locality? Now, a basic fact about gravity, which sets it apart from the matter interactions, is the fact that it's non-renormalizable. At one loop, this calculation was done by Toft and Feldman already long ago. And it turned out that at least without matter, it is renormalizable. But at 2 loops, there appears this counter term, which was calculated by Grof and Sagnotti and Van der Ven long ago. And in fact, at higher orders, you will have even more of these terms required to make finite predictions. At this point, there are 2 possible conclusions. One is, if I may say, the attitude of the non-string community. These people claim that the divergences are simply an artifact of the perturbative treatment, and that they will eventually disappear upon proper non-perturbative quantization of the theory. The other point of view, embodied by string theory and supergravity, is that one must somehow modify Einstein's theory at short distances in such a way that these divergences disappear. Now, no matter what your point of view on this is, I think no one can claim, no approach to quantum gravity can claim complete success that does not explain in all detail the ultimate fate of this divergence and how it is removed. Well, there are many approaches to quantum gravity. I cannot possibly present any overview of this, so let me just say to spend 2 slides on canonical quantum gravity, because this was the first approach. It's already been mentioned or come up in some previous talks. This is basically applying textbook quantization procedures to Einstein's theory directly. This was developed originally by Dirac and then other people. Here you sort of view the space-time geometry as the evolution of a spatial geometry in time. So you have a dynamical system that follows Einstein's equations. And the dynamical variables are here the spatial components of the metric here and their associated canonical momenta. And in fact, this program leads to a kind of Schrödinger equation of quantum gravity. This is the Wheeler-DeWitt equation that already came up in previous talks, especially in Alex Vilenkin's talk this morning. So he wrote it out schematically. Here it is written out in full detail for pure gravity in 4 dimensions. So this is an equation for a wave functional psi of g, which depends on the spatial components of the metric, and this is what people refer to as the wave function of the universe. So you might say, well, we've had this equation for 50 years, so why don't we just take it and solve it and study it? Now, there are numerous problems with it that have sort of obstructed progress here. First of all, on the mathematical and technical side, the Wheeler-DeWitt equation is mathematically not just ill-defined, it's very ill-defined, even by the sloppiest standards. And you might say that this is just, it's just that the non-renormalizable infinities reappear in a different guise. There are recent attempts to sort of overcome the mathematical difficulties, and this is what loop quantum gravity and these approaches are based on. They replace the metric variables by quote-unquote new variables. Then the problem is sort of appears in completely different guise. Now, I personally do not believe that a mere change of variables will solve the problem, but you might say that in some sense jury is still out on this issue. But there are also numerous conceptual issues that we've heard about yesterday. Jim Hartle beautifully explained, the issues of Copenhagen versus Everett, or how should we interpret quantum mechanics in the cosmological context. We had talks about quantum cosmology, and the one feature which I would like to emphasize once again, it was also emphasized by Alex in his talk, is the fact that actually the Wheeler-DeWitt equation is a timeless equation. It's a constrained equation, one for every spatial point, but there's no time in this equation. So it's like a stationary Schrödinger equation, but with a 0 on the right-hand side. So it's the question of how does time emerge from this? And this is something that might start you wondering about, is the usual formalism, mathematical setup of quantum mechanics, is this enough, or will we need something else? For example, if you think about things like unitary evolution, you need some notion of time. I would say that time is a relative concept in general relativity, and therefore the equation cleverly takes note of this by simply not depending on any time variable. Now the question, there are 2 approaches to this. Further, like loop quantum gravity to try to massage this equation to something else. Or otherwise, you say, well, maybe the equation is correct, but maybe not with this particular Hamiltonian. So then the question is, which is the correct Hamiltonian constraint operator, Wheeler-DeWitt operator? Now, in the rest of the talk, my point of view will be that we should exploit symmetries to answer this question. So this was already alluded to in the previous talk. So the main emphasis in the rest of my talk will be on symmetries, which are really an essential element also in superstring theory and all the things that we do. Now, supersymmetry is an extension of ordinary symmetry in the sense that you also have now supercharges as symmetry generators, and they obey anti-commutation relations. And as we heard in the previous talk, so I've just written the basic, one of the basic relations here, that two supercharges commute to a translation. You can have n supercharges where this index I runs from 1 to n. And as we heard in the previous talk, for global supersymmetry, the limit is n equals 4. And for local supersymmetry, the limit is n equals 8. Now, one thing that people were excited about in the beginning about supersymmetry is not the hierarchy problem, but the fact that it allowed to circumvent the Coleman-Mandula theorem forbidding the merger of space-time and internal symmetries. This was much discussed. But I would like to emphasize this is only true for n extended supersymmetric theories, not true for n equals 1 supersymmetric theories, which are theories that are currently being tested at LHC. So that's supersymmetry. We'll get back to this. And the other kind of symmetry that will now feature in my talk is duality symmetry, whose first incarnation was found by Dirac long ago. He noticed that Maxwell's equations in empty space are invariant under complex rotations of a vector where you combine the electric and the magnetic field with a factor of I into a complex vector field, and then you rotate it like this. This invariance has turned out to be, these dualities have turned out to be of extreme importance in supergravity and superstring theory, because we know what happens is that we now have to deal with generalizations of these symmetries to matter couplings, not just electromagnetism, but also to matter couplings in gravity. Actually, one of the unsolved problems is how to dualize Einstein's theory at the non-linear level. Anyway, dualities, as I said, are ubiquitous in supergravity and superstring theory. So I would also like to say, why supergravity? Well, this is a well-known textbook argument that local supersymmetry implies gravity. And this is simply, if you think about, if you multiply the generators by parameters, supersymmetry parameters, and look at the algebra, then you get a translation, but the translation for local supersymmetry will be x dependent on where you are. So what you get here is a local translation, but a local translation is an infinitesimal diffeomorphism. Hence you immediately are in the framework of general relativity. The gravitino field that's the associated gauge field associated to these local supersymmetry transformations, because it transforms like this. So this is the the gauge field of local supersymmetry, and the associated gauge theory is supergravity. So I will not show any Lagrangian, unlike Lars, whose Lagrangian was rather simple. Supergravity Lagrangians are usually very messy and fill at least one of these pages, so I will not show them. But just emphasize that these theories become more and more restricted as you go up in the number of n, in the number of supercharges. And once you're beyond n equals 4, there are no more matter multiplets, and you have essentially unique theories. There's been a whole development here to how to best formulate these theories, and one is based on superspace. I've already mentioned it in connection with gravity versus matter, where you extend the space-time by fermionic coordinates. And well, we think about this sometimes classically by taking these as anti-commuting objects, elements of a Grassmann algebra. But as David also emphasized yesterday, this is really like adding quantum dimensions, because fermions are the quantum objects par excellence. There's no real classical analog of a fermion. So once you do this, you're automatically in the quantum domain. Now, before passing on, yes. So here's a brief survey of what this has, what we have learned over the last 45 years or so, and how we apply it to quantum gravity. Here, the basic strategy is to render gravity perturbatively consistent by modifying at short distances, by canceling UV infinities. A nice feature here is that in this way you you have some reason for including matter. The non-string approaches very often have this strategy of, you know, just starting with Einstein's theory, quantize that, and once you've solved it, then you do the matter fields. Here you have real reason for matter, why there's matter in the world. And then you have the maximally symmetric point field supergravities, point field theories, n equals 8 in 4 dimensions, or its ancestor in 11 dimensions. That's 11-dimensional supergravity. Now, superstrings, extended supersymmetric objects, this is what Lars has reviewed, so I will not say very much on it. And there's also probably something beyond superstring theory, call it M theory, matrix theory, ADS-CFT, supermembranes. We really don't know what the really non-perturbative formulation is of this theory, or if you like, what the Lagrangian is. Is there a Lagrangian? This we don't know. Now, before passing on, let me just say, because this is much discussed these days, that the great disappointment of many people, low energy supersymmetry has not shown up at LHC. It's quite possible that it's not there. So this means we have to sort of reset all of our thinking about the standard model in some sense, how to go beyond the standard model. And I think the key problem, and this has been around for 40 years since the very beginning, the question is, how is supersymmetry broken? It can be arranged, although not very compellingly, I think, in supersymmetric field theories or supergravities. But you know, in string theory is also a problem. And I would also like to mention that supersymmetry is not compatible with a time-dependent cosmology, in particular also not with a positive cosmological constant. So the question is, you know, what's the role of supersymmetry in, you know, with all these facts? There's positive cosmological constant. We don't see any of this at LHC. So it could just mean that we have to think about applying supersymmetry to nature in a different way. Now, here's one thing that I would like to emphasize in particular. You know, if you think about quantum gravity and emergent space-time, the question is, what's the role of space-time supersymmetry? Space-time supersymmetry relies on concepts that need space and time. You know, the very notion of a space-time fermion depends on that you need, that you have some kind of... So the question is really, you know, do we need to modify these concepts if we really want to understand things from an emergent space-time perspective? So here I say distinction between space-time bosons and fermions may become actually meaningless in a pre-geometric regime. So n equals 8 supergravity, this is the theory that Lars already mentioned. This is the particle content, which was already shown by Lars. This theory has the expected symmetries. I will not show you the Lagrangian, but it certainly has the symmetries. These symmetries more or less uniquely fix the theory what it is. But perhaps the most important discovery in this context was by Kremer and Gilliard, the fact that on top of the expected symmetries, the theory exhibits a nonlinearly realized or hidden duality symmetry with the exceptional group E77. And this is exactly the kind of symmetry that of the type that I talked about or mentioned when I said the kind of symmetry that Dirac had discovered, namely relating electric and magnetic fields. And this is exactly how the minimal representation of E7 is 56, but you only have 28 vector fields, so you need to combine the electric and the dual magnetic vectors in one multiplet, as it were, to realize that symmetry. So this was also important to actually construct the Lagrangian of the theory. Without this, you would not have been able to work out the Lagrangian of this theory. And in fact, after this discovery, it became clear that there's a very close connection between these exceptional Lie algebras and extended supergravity theories. So what are the main issues here? And one was already touched upon by Lars. I mean, this question was there from the beginning, and we still don't know the answer. The question is whether theory is really actually ultraviolet finite to all orders, And the other question is, of course, does it have anything to do with real physics? That is the question that people asked at the very beginning. Murray Gelman was one of the first. So here's a sort of list of things that have been discussed, have been around for a long time, like the on-shell form. There's a manifestly supersymmetric formulation of the theory in superspace. When it comes to counter terms, one of course has to ask the question, what is, does the presence of this E7 somehow affect the finiteness properties? Can you exploit E7 perhaps to show that it's finite? So this has been tried for a long time. Again, the answer is not yet known, but the one thing I can say that at this point there's no counter term known in this superspace formulation that is fully compatible with the nonlinear supersymmetry and nonlinear E7. This is, there had been all kinds of proposals over the years, but the problem here is because we're somehow on shell. You have to modify, once you add a counter term, you also have to modify the E7 in a very complicated and nonlinear way, and there's no one so far who has been able to do this. But there have been some recent developments that were also already alluded to in last talk. There's amazing work here by these people who have actually been able to do calculations that I wouldn't have thought possible 30 years ago. And they've shown that the theory is actually much more finite than expected. And so far, actually, it's been shown up to 4 loops that it behaves exactly like n equals 4 Young-Mills. And the question is, does this continue? So they're currently involved in checking 5 loops. This is really mind-boggling. There will be no divergence at 5 loops, but what they want to check is the predictions for the onset of divergence. So this is the prediction for n equals 4 Young-Mills, and this is the old prediction for supergravity. And when you substitute L, they do this in dimensional regularization, so you can check as a function of dimension where the divergences will start. So if you put L equal to 5, which is they're now doing, you have 2 possibilities for the onset of divergences. If it's Young-Mills, then it's 26/5. If it's this old supergravity, it's 24/5. So we won't see the divergence, but I think then if it's this, then superstring people will cry victory and say, well, n equals 8 is not finite. If it's this, I will cry victory. But anyway, no matter how it is, the question is, even if the theory is finite, I mean, you will not be able to prove this by explicit calculations. This is beyond, even with this very advanced technology, beyond what you can do. But the reason some people have doubts or think it must diverge at some point is that there's no obvious reason why this theory should be finite. If it is finite, then it has to do with must have to do something with an unknown symmetry. Now there's some other aspect which is little known, but I would like to emphasize this, especially now that LHC does not discover new spin 1/2 degrees of freedom. This is an old idea of proposal of Gelman's to identify the fermions of the standard model with those of n equals 8 supergravity. There's a very strange coincidence. N equals 8 has 56 spin 1/2 fermions. You take away 8 Goldstinos to break the supersymmetry, you're left with 48, which is exactly the right number, including right-handed neutrinos. So on this issue, I side with Cecilia because right-handed neutrinos must be part of the story. So what Gelman proposed, he noticed that you have this SO8 symmetry in n equals 8. You can break it like this. The first idea was to identify this with color, and this doesn't work. And then he had this very strange idea of introducing a family symmetry on top of color symmetry and identifying this SU3 with a diagonal subgroup of this SU3 color and a hypothetical SU3 family. So if this works, it would actually explain why there are 3 families. So it matches, and if you look at the electromagnetic charges, he noticed that actually it almost works. It's just that these electric charges are systematically off by 1/6. So this has been around for 30 years, and it's only, I at the time I thought this is probably a mirage, and well, it doesn't work. But we've now recently actually figured out a way to remedy this mismatch, to get the right charges by deforming the U1 that appears here. But it turns out that this deformation takes you outside of n=8 supergravity. So if there's any matching that might work, then it's clear it cannot be within n=8 supergravity. So even coming from supergravity, being supergravity aficionado, it's very clear that, it seems clear also from that point of view, that something beyond field theory is needed. I mean, in string theory we would say it's needed for finiteness, quantum consistency. There's also a question even if it's finite, you don't know what. The questions I posed at the beginning about the structure of space-time, the smallest case, are not really answered here, and so here the standard quantum gravity issues are still open in some sense, even if it's finite. However, as I said, I would put symmetries to the fore, and so in further, following up this line of development, I would take the hints from this unexpected Crémer-Juliat symmetry of n=8 supergravity. Well, after the discovery, I said it became clear that there's a very intriguing connection with all the exceptional Lie groups. All their non-compact forms, real forms, appear in extended supergravities. And in particular, when you do this in other dimensions, you also find exceptional groups. And there's this rule that relates the rank of the group to the dimension. So in 4 dimensions, it's E7, and in 3 dimensions, it's E8. Which is something that sort of prompted Bernard Juliat already a long time ago to conjecture, why doesn't it go on like this? And in fact it does. You can show that if you go to 2 dimensions, it becomes infinite dimensional. This is a generalization of what's called the Garrosh group in general relativity. It's a solution generating symmetry, so it's an infinite dimensional symmetry. The moduli space here is the moduli space of axisymmetric or plane wave solutions of 11-dimensional supergravity. And going one step further, you go to E10. And already E9 is infinite dimensional. This is much more infinite dimensional. I will show a picture so you get at least an impression of what this is. So we think that somehow this could also tell us something about what happens to space and time in the quantum regime. So what is this? This is the maximally extended hyperbolic Kac-Moody algebra. Well, you would think, is this a symmetry after reduction to 1 dimension, where you drop all dependence on all coordinates except the time coordinate? You would think in this reduction what you get is a very simple system. If you take the supergravity Lagrangian and stipulate that things only depend on time coordinate, you're left with a kind of mechanical system. So that wouldn't see. It's somehow astonishing that you should have so little such a huge symmetry realized on such a simple system. And it is here actually that we make the connection with some other initially completely unrelated development, namely analysis of BKL, Belinsky, Khalatnikov, Lifshitz, of behavior of Einstein's equations in a cosmological context near a space-like singularity. This is important. This only works for space-like singularities. And they hypothesized, because you've seen this picture in the connection with inflationary universe, the decoupling of spatial points and so on, which led them to hypothesize there's actually a decoupling as you approach the singularity. There's a decoupling of spatial points, which means it's an effective reduction to 1 dimension that happens at the singularity, which suggests that maybe it is at the singularity that you really start seeing the full symmetry of this system. Now, I have no time to tell you what E10 is. because I don't know what it is. But anyway, there's a sort of way to generate it. To it is well defined, definitely. It's well defined in terms of a Dynkin diagram and certain rules how to generate the algebra. But I think to get just a more visual impression of what this algebra is, you should look at this picture. This is a slice through this was done by one of our former postdocs, Teke Nutma. This is a slice to the root space of E10. This is somewhat, if you've ever seen the Meson octet diagram, it's a very nice diagram. Each point on this diagram is associated with an independent symmetry transformation. Same is true here. You see, you can hardly see the points, but each point is associated with one or more independent symmetry operations. And in fact, this is not all, because the algebra, when you decompose it, will expose infinitely many such layers. And the deeper and deeper you go into it, there will be an exponential growth in the number of symmetry operations. So to understand the mathematics of this thing, which is not understood, is, I would say, a challenge on a par with quantum gravity. Because in physics, if we claim that this is a symmetry of the system, you will have to somehow figure out what is the meaning of these transformations, what do they act on, what are the states, what are the objects. And we think that, we have no idea how to do this, because mathematicians, even after 45 years, haven't been able to figure out or produce a more tangible realization of this algebra. But we think that in there is some deep information, maybe even about M theory. So this is what, this is the other thing why E10 is good, because it sort of contains all the duality symmetries that we've seen before. In particular, if you try to combine 2A and 2B supergravity, or their duality symmetries, you immediately you get something like in the picture on the previous page. There's no way of avoiding this if you try to unify this from the symmetry point of view. So this is what we're trying to do with Thibaut Damour, Marc Guénaud since 2002, and Axel Kleinschmidt. The conjecture is somehow that here space-time, as you approach the initial singularity, the classical space-time somehow gives way to, something else, which we really don't know what it is. And that the theory should quantize near the singularity is really this other theory that's somehow defined by this infinite dimensional symmetry. And then the question is, how does space-time, classical space-time, emerge out of this? So I have two more slides. So let me just summarize main points and challenges. So the duality symmetries have turned out to be far more important than was even expected at the beginning. They're absolutely crucial for most of the things we do in supergravity. There are many different aspects to this, but they're absolutely crucial to supergravity, and I would say string theory. So you might say that in some sense this is more important than space-time symmetries, and this is a kind of symmetry that might even work in a regime where there's no more space and time to talk about. As I said, E10 encompasses previously known dualities, unifies them with maximal supersymmetry, but the question we've not made any progress on in 15 years, it's really hard, is the question, how does the emergence of space and time really work near the singularity? It would somehow involve, doing away with space and also ultimately time in the Wheeler-DeWitt sense, and somehow spreading this information that's contained in the spatial dependence, somehow spreading it over this monstrous Lie algebra. And as I said, we haven't been able to, it seems extremely hard. We have not really made, the thing is such, up to a point it works beautifully, perfectly. We can reconstruct Lagrangians of 11-dimensional supergravity just by using E10, and same for others. And if you slice E10 in different ways, you recover all the other supergravities, maximal supergravities. But I think that in order to really do this, quantum theory is probably required. Somehow you think, you cannot understand this without bringing in quantum theory in an essential sense. Now, a particular focus of recent work has been to the understanding of fermions. They are not governed by E10, but the maximal compact subgroup, which is something called KE10. This is not even a Kac-Moody algebra. It's something, different. In fact, something we know not very much about. But this is in some sense, if I boast a little bit, I would say this is a candidate for the R symmetry of M theory. And finally, I talked about matching or correcting this 1/6 mismatch in this Gelman scheme. In fact, you can show while this deformation that I mentioned is not in SU8, with Axel Kleinschmidt, I've shown that actually it is in KE10. In fact, KE10 is big enough to contain all standard model symmetries, including it also has chiral action, so there's some potential for the emergence of chiral transformations as well as family symmetries. There's some interesting connection between the Weil group and some work that Pierre Ramon has been doing in recent years on understanding family symmetries. So there are all kinds of very intriguing links, but they're also very hard problems. So here's my summary. What really I think is strongest argument for quantum gravity is the incompleteness of standard model and general relativity. And one way to approach the problem is to look how short distances are resolved. There are various proposals on the market, most prominently, of course, string theory. But maybe also it's that n=8 supergravity is actually finite, and then there are other ideas which one can discuss. So here in this talk I've sort of advocated symmetry and enhancement as the best strategy for this search. So thank you very much.
We were told many, many years ago that exceptional groups went up only to up to E8. Yes. Now you said E10, I was shivering. And of course, I just wonder, is there also E11, 12, yes. 13, 14?
Yes, that's true. I mean, it's true that E8, the finite dimensional ones stop at E8. That's been known for 100 years. And anything beyond is infinite dimensional. And yes, you can go on beyond E10 to E11. That's Peter West's proposal, E12, E13. But the thing that makes E10 unique, it's what's called a hyperbolic Kac-Moody algebra. And hyperbolicity is a mathematical restriction that basically means that if you take away a node from the Dynkin diagram, you should be left with finite or affine. And then it's at the end of the line. And the intriguing thing is really that this purely mathematical criterion, which has nothing to do with physics at first sight, actually matches exactly with a maximal supersymmetry. So, what it really means, I don't know, but I think if there are two such things that are completely disparate at the beginning and then you find such a connection, there must be something there.
Yeah, Hermann, I've always been intrigued by the fermions being in an obvious 16 representation of SO10.
Yes.
Now that's different from what you're saying.
Yes, yes, it's somewhat different.
Way, but the natural thing, the natural thing there is that the fermions are in the same representation as they are in the Lorentz group. So really, it's an SO14. Now I don't know what to make out of that.
Well, that's I must say I also don't quite know what to make of it. I agree with you that. The fact that the fermions fit into 16ths of SO10, that's perhaps the best, strongest argument for grand unification. But what you're here aiming for is not just, within one generation, but we're actually looking for a scheme that could accommodate also family symmetries. And one of the things about this Gelman idea, which intrigued me from the very beginning, is that, if you look at these assignments here, this is something very strange. If you look at up and down quarks, and you look at the assignment of family symmetries, you see that it's a 3-bar and the 3. So that means that this family symmetry would not commute with the electroweak symmetries, with the electroweak SU2. And I've always meant at some point, if I ever met Gelman again, I wanted to ask him, how did you get the idea? Because the family doesn't commute with the weak interactions. So there's something really, really strange here, and so I don't know what it means.
Okay, so I think now it's